Most people step right over the most common form of gold-bearing quartz. It doesn't shimmer. It's not crystalline. It looks like an ordinary chunk of opaque white rock, often weathered and rounded at the edges. Yet time and again, some of the richest free-milling gold finds have emerged from plain milky quartz fragments, sitting idle in creek beds or weathered slopes. What's missing is not the gold, but the trained eye to see its context. In gold-bearing terrains, especially those shaped by ancient hydrothermal activity, quartz often forms veins that cut through older rocks, sometimes miles across. When these veins cool, they trap trace metals, including gold, between their silica lattices or in voids and fractures. Not all quartz hosts gold, but nearly all naturally occurring gold in hard rock settings is associated with quartz. What separates one from the other isn't just look, it's placement surrounding minerals and weight. Milky quartz, for instance, is a product of fast cooling, trapping minute inclusions, and often lacking transparency. While clear quartz is favored in jewelry, it's the milky kind that often carries microscopic flakes of native gold, especially in areas where faulting and pressure have created zones of rapid mineral deposition. In some cases, free gold occurs as dust or wires along fracture lines, requiring crushing to expose. In others, it's bound within pyrite or arsenopyrite, detectable only through indirect clues. During field surveys, one missed signal is quartz float, loose chunks of quartz that have broken off a vein and been carried downslope. Many ignore these because they look disconnected, but tracking float uphill, especially when associated with rusty staining or small sulfide specks, often leads back to source veins. One prospector in California's Sierra foothills traced a trail of milky float up a ravine and, after a sequence of crush tests, exposed a quartz vein that assayed over 3 ounces per ton, rich by any standard. To the untrained eye, gold-bearing quartz looks indistinct, but a few sensory indicators stack the odds. A slightly heavier feel, orange or red oxidation, angular fractures, or a granular texture. Sometimes the quartz will contain tiny pits or cavities where sulfides have weathered out, an indirect clue of their past presence. Even slight magnetism in the host rock, from residual magnetite or pyrite, can tip the balance toward a gold-bearing system. Yet the true test begins not in visual inspection, but in hypothesis. Is this quartz part of a larger system? Is it in a known gold district? Are other indicator minerals nearby? With even a basic hand lens and a magnet, the next step becomes clearer, separating the truly ordinary from the quietly extraordinary. The difference between barren quartz and auriferous quartz often lies in just a few overlooked visual traits. Most novice rockhounds focus on clarity or shine, assuming visible gold or glitter signals value. But gold rarely presents itself so clearly. Instead, it embeds along microfractures, coats internal voids, or exists as invisible particles locked inside sulfides. The real field advantage comes from recognizing patterns of color, structure, and texture that repeat in known productive zones. Start with luster. Gold-bearing quartz typically shows a dull to greasy luster rather than a glossy shine. Milky quartz, a dense, white or gray opaque variety, is especially promising when it carries rusty or orange-stained surfaces. These iron oxide coatings often form as pyrite oxidizes at the surface, a process called Gaussian formation. In some cases, what looks like surface dirt turns out to be oxidation, halos hinting at the prior presence of sulfide-bound gold. Next is translucency. While gem-quality quartz is prized for clarity, most auriferous quartz is cloudy, granular, or zoned. Look for quartz that transitions from clear to white or white to smoky across growth bands. This zoning often records fluid pulses during vein formation, each pulse a potential gold deposition event. Smoky quartz, especially when darkened near fracture lines or coated in limonite, has been associated with late-stage gold events in shear zones. Surface texture adds another clue. Vuggy or porous quartz, marked by tiny cavities or etched-out pits, can indicate leached sulfides. These voids are often surrounded by iron staining or greenish mineral coatings, like chlorite or epidote. Similarly, brecciated quartz, showing angular fragments cemented by later silica, signals a dynamic depositional environment with multiple mineral pulses. These are prime candidates for closer testing. A special case worth noting is ribbon quartz, alternating bands of milky and glassy quartz in parallel layers. This texture often marks repeated fracturing and fluid infusion, common in mesothermal vein systems. In gold regions like Nevada, California, and the Pilbara, ribbon quartz with iron oxide coatings has frequently yielded rich free gold once crushed and panned. Inclusions also matter. Fine-grained pyrite, chalcopyrite, or arsenopyrite within quartz can be visible as silvery flecks, dull brassy masses, or dark metallic grains. These aren't valuable themselves, but their presence points to the type of hydrothermal chemistry that often carries gold. Arsenopyrite in particular, steely, sharp-edged crystals often aligned with vein planes, has strong statistical correlation with gold mineralization in shear zones and greenstone belts. Lastly, observe fracture patterns. Quartz with sugary granulation or Hackley breaks may be more friable, easier to crush and test for embedded gold. Also important are pressure solution textures, where quartz seems smeared or warped under directional stress, often in fault zones. These deformation features increase the chance that gold precipitated into microfractures as the quartz sealed. It takes time to train the eye, but these subtle traits, staining, zoning, texture, and association, form a diagnostic picture. Even in the absence of visible gold, they can stack up to a high-probability target. Still, glancing inspection can only go so far. What separates an interesting rock from a payable find is what comes next. Reading its position in the terrain. Gold doesn't simply appear in quartz. It travels through it. Understanding how quartz forms veins is central to knowing where gold hides and why it concentrates in certain zones. Quartz is a dominant gangue mineral in hydrothermal systems, networks of hot, mineral-rich fluids that penetrate fractures in the Earth's crust. As these fluids cool, quartz precipitates, often trapping metals in the process. Where, how, and when those fluids move determines if the resulting vein holds visible gold, submicroscopic particles, or nothing of value at all. Three main types of quartz vein settings matter most for gold hunters: lode veins, stockworks, and ladder veins. Each one gives different clues in the field and requires different sampling approaches. Lode veins are what most prospectors think of: relatively linear quartz bodies, often several centimeters to meters thick, cutting through bedrock. These veins can persist for kilometers and often follow fault lines or shear zones. Gold in lode veins is typically associated with coarse crystalline quartz, visible sulfides, and fracture-controlled deposition. In historic gold camps like the California Mother Lode, entire towns were built around these features. Stockwork zones are more chaotic. These consist of dense networks of tiny intersecting quartz veinlets, sometimes dozens per square meter, forming a mesh-like structure in altered rock. Gold here is often microscopic and locked in sulfides, requiring bulk sampling and milling to assess grade. The famous Carlin-type deposits of Nevada are examples where stockwork systems, though visually unimpressive, yield massive returns through processing. Ladder veins are smaller, regularly spaced quartz infillings that occur perpendicular to major shear zones or fractures. They resemble rungs on a ladder and often record repeated episodes of mineralization. Because gold-bearing fluids follow these microfractures during periods of tectonic stress, ladder veins can be extremely rich on a small scale. The visible width might only be a few centimeters, but gold values can be concentrated and high. Field observation of vein geometry matters. A quartz vein that parallels foliation or bedding in the host rock is less likely to be mineralized than one that cuts across it. Cross-cutting veins suggest they formed later, potentially during a tectonically active gold-forming event. Additionally, veins that widen or blow out at bends or intersections often serve as depositional traps for heavier metals like gold. Vein margins also deserve scrutiny. Alteration halos, zones of yellowish or bleached rock adjacent to quartz, suggest chemical reactions between hot fluids and host rock. These reactions can liberate or trap metals, depending on fluid chemistry. In productive systems, these halos often contain disseminated sulfides and finer gold even beyond the visible quartz. Another overlooked detail is splays, small offshoots from a main quartz vein. These can contain richer gold concentrations than the central vein, especially if they represent a low-pressure site where fluids slowed and dropped their load. Many amateur prospectors fixate on the biggest vein and miss these splays, which may be hidden just under overburden. Finally, weathering alters the field picture. Near-surface quartz may appear pitted, iron-stained, or completely barren of metal clues. But deeper down, the same vein could host visible gold or dense sulfide zones. Understanding vein continuation beneath soil or regolith is part of the prospector's edge, and often requires trenching, metal detection, or probing with a hammer and hand lens. A clean quartz vein tells little. A stained, sulfide-laced one whispers secrets. When gold rides through quartz, it rarely travels alone. It's usually accompanied by an entourage of indicator minerals. Among these, pyrite, arsenopyrite, chalcopyrite, and galena stand out as the most statistically reliable companions. Their presence doesn't guarantee gold, but in the right setting, they significantly raise the odds. Pyrite, the ubiquitous fool's gold, is the best known and most misunderstood indicator. Often forming cubic or granular masses within quartz, it's easy to mistake for value or dismiss entirely. But context matters. In gold systems, pyrite often serves as a carrier or substrate for microscopic gold, especially when it's fine-grained and dispersed. A single gram of pyrite may host invisible specks of gold, detectable only with an assay or leach test. In the field, freshly broken pyrite shines pale brass. Weathered, it leaves rusty red stains on the quartz surface, oxidation halos that linger even after the sulfide has leached away. Arsenopyrite, however, is far more reliable. This silvery gray mineral often forms elongate, striated crystals along quartz vein boundaries or fracture planes. It's especially common in mesothermal and orogenic gold deposits, major sources of hard rock gold. Unlike pyrite, arsenopyrite weathers to a dull yellow or greenish crust and can give off a garlic-like odor when struck or ground. A rock containing arsenopyrite may not sparkle, but in regions like Ghana, Nova Scotia, and parts of the Yukon, its presence has historically correlated with gold-rich zones. It's not always visible in hand sample, sometimes just a metallic sheen under a loupe, but its geochemical signature is unmistakable. Chalcopyrite, a copper-iron sulfide, can also occur alongside gold, especially in polymetallic systems or contact zones. It has a brassy yellow appearance with iridescent tarnish and a softer feel than pyrite. While less diagnostic on its own, when found with quartz and arsenopyrite, it often signals the kind of fluid chemistry capable of carrying gold. Look for chalcopyrite in veins with greenish or blue halo zones, evidence of copper alteration. Galena, a lead sulfide, appears in some high-temperature quartz veins, especially where silver and gold occur together. Its heavy, metallic gray appearance and cubic habit make it easy to spot. While galena itself is usually mined for lead or silver, its presence in quartz veins sometimes coincides with gold-rich pockets, particularly in deeper vein systems or contact metamorphic settings. Iron oxidation halos deserve special attention. When sulfides like pyrite or arsenopyrite degrade under surface conditions, they produce limonite, goethite, and hematite, soft iron oxide minerals that stain quartz in shades of yellow, orange, red, or brown. These surface stains are a free field guide. They often mark zones of previous sulfide concentration and therefore potential gold association. One trick: scratch the stain with a steel blade. If the orange layer rubs off to reveal hard, unweathered quartz beneath, it likely originated from pyrite or similar mineral decay. If the quartz fractures reveal fine cubic holes or cavities, sulfides were almost certainly once present. Another subtle clue: boxwork texture, a honeycomb or lattice-like structure left behind after sulfides dissolve. These voids, often preserved in weathered quartz, can be stained but still visibly geometric. This pattern is a telltale sign that metallic minerals once filled those gaps, and possibly took gold with them. Despite these indicators, not every sulfide-rich quartz is valuable. Some deposits are sulfide-heavy but gold-poor, especially in volcanic settings. That's why sequence matters. First, observe, then test for magnetism. Pyrite, a magnetic iron sulfide, can suggest deeper mineralization. Then crush and pan to check for free milling gold. If that fails, chemical testing or lab assays become the next step. A quartz vein tells a story, but its position in the landscape determines whether that story ends in gold. Many field collectors focus too closely on what the rock looks like in hand, missing the broader structural clues underfoot and overhead. Orientation, contact relationships, and host rock alteration can point directly to zones where gold concentration increases, or where it never had a chance to form. The first critical clue is vein orientation. Productive quartz veins often cut across the natural layering of host rocks, what geologists call discordant. These cross-cutting features suggest mineralization occurred after the country rock formed, often during regional tectonic or thermal events that also drove hydrothermal fluid movement. A quartz vein that follows bedding planes or foliation is less promising unless it's part of a broader shear-hosted system, where the bedding itself has been reactivated by deformation. More promising are shear zones and fault intersections, where repeated rock movement has opened fluid pathways. Here, quartz veins may show evidence of multiple episodes of mineralization. Fine-grained early quartz cut by coarser later quartz, often with sulfide bands along the boundaries. These are known as composite veins and often host the richest gold pockets. Look for stepped fractures, rotated blocks, and slickened sides, polished fault surfaces nearby. These signs mark areas of prolonged fluid movement, a critical precondition for gold deposition. Fracture density also matters. High concentrations of hairline cracks or cross veins within the host rock may indicate a broader stockwork system, where mineralizing fluids percolated through a network of microfractures. In such systems, gold may not be visible, but it can still occur in recoverable amounts through bulk processing. When quartz float or outcrop displays crisscrossed veinlets over several square meters, it signals a need for systematic sampling, not just a single grab test. Next is the relationship between quartz veins and wall rock alteration. Productive veins often show a visible alteration halo extending outward into the surrounding rock. This can range from subtle bleaching, silicification, to vivid colors, reddish hematite, yellow-orange limonite, or green chlorite epidote. In some cases, the alteration zone contains more gold than the quartz itself, especially in disseminated systems where metal deposition occurred across a diffuse front rather than a narrow vein. Also key is the type of host rock. Some rock types are more chemically reactive with gold-bearing fluids and can create conditions for deposition. For example, carbonates like limestone and dolomite often develop contact zones rich in iron and silica, favorable traps for gold in replacement-style deposits. Similarly, ultramafic rocks, such as serpentinized peridotite, can host gold along their contact zones with more felsic intrusions, particularly when quartz veining is present. Even subtle shifts in terrain can be revealing. For instance, a quartz vein that thickens as it approaches a fold hinge or fault bend may indicate a dilation zone, an area where pressure drops allowed fluids to deposit metals. These widened sections can become chutes, where gold is concentrated over short vertical or lateral intervals. Observing where a vein suddenly changes direction, bulges, or splits into multiple strands may lead directly to higher-grade pockets. Loose material underfoot, quartz float, also gives clues. Float that shows a directional trend, aligned pieces uphill, can be traced to its source outcrop. Experienced prospectors walk float lines upslope, checking for changes in stain, weight, or sulfide content. Where the float thickens or becomes angular, it's often close to the bedrock vein. Finally, pay attention to groundwater staining. In active stream beds or hillside seeps, iron-stained water or red-brown sediment often emerges from sulfide-bearing quartz zones. These natural weathering indicators can trace back to rich veins just beneath the surface. The landscape doesn't lie. It records the path of the fluids that formed the quartz and the gold. By learning to read that path, a prospector doesn't just hunt rocks. They reconstruct events deep in Earth's crust, unlocking the structure behind the sparkle. No matter how promising a quartz vein looks in the field, gold means nothing unless it can be separated and recovered. That's where crush and pan testing comes in. A low-cost, high-impact method to prove whether gold is actually present. Free milling gold, the kind that's not chemically bound in sulfides, can often be liberated by simply crushing quartz to powder and panning the concentrate. And yet, many overlook this step, relying on guesswork instead of proof. The process starts with sample selection. A good rule is to collect a kilogram or more from the most mineralized portion of the quartz vein, especially areas with visible sulfides, iron staining, or fracture zones. Avoid weathered surfaces unless specifically testing oxidation halos. Fresh material broken from the interior gives the most accurate result. Multiple subsamples from different parts of the vein help reveal distribution patterns. Gold often occurs in pockets, not uniformly. Crushing is key. A hand sledge and steel mortar work well for small samples. For more efficient processing, a manual jaw crusher or heavy-duty pestle speeds the breakdown. Quartz is around 7 on the Mohs scale, harder than most rock but brittle, so it breaks into angular fragments before reducing to powder. The goal is to reach particle sizes around 1 millimeter or smaller, exposing any enclosed gold. Once the material is powdered, it's ready for gravity separation by panning. Use a gold pan or batte with water to concentrate the heavies. Wash away the lighter silica until only dense particles remain. In productive samples, even a few specks of yellow metal, flattened, malleable, and bright, signal success. True gold won't float, won't shatter under pressure, and maintains a soft-edged shape under a loop. If the sample leaves behind fine metallic flakes that smear under a fingernail or resist crushing, they're likely gold. Color and behavior matter. Gold is butter yellow under natural light, but in tiny quantities, it can appear dull or reddish due to alloying with copper or silver. One common false positive is mica, especially biotite or phlogopite, which shimmers but floats and breaks easily. Another is chalcopyrite, which has a brassy yellow tone but quickly darkens and is brittle when tested. True gold feels soft and pliable, often flattening into a plate during the crush. In some cases, gold isn't visible even after panning, but if the pan still shows black sand concentrates, typically magnetite or hematite, it's worth sweeping with a magnet to isolate the magnetic fraction. Then repan the non-magnetic material slowly. Fine flour gold can hide among heavy minerals and take multiple cleanouts to reveal. Patience pays. Some quartz samples yield only a few grains of gold, but those grains might extrapolate to ounces per ton if the system continues. If repeated samples from a quartz vein produce consistent gold in pan, it's a strong signal of a free milling system. This is the ideal target: gold that requires no roasting, leaching, or chemical extraction. In historic hard rock mining regions, these are the veins that powered stamp mills and early rushes. Even today, a free milling sample that returns 1 gram per ton or more is worth further evaluation, especially if the vein is accessible and consistent along strike. But not all quartz gives up its gold this way. In some systems, gold is locked within sulfide grains or occurs in microscopic sizes invisible to panning. That's when more advanced methods become necessary: fire assays, cyanide tests, or spectrometry. But for the field prospector, crush and pan is the first filter. It's simple, repeatable, and can be done on site with basic gear. Not every promising quartz sample shines. Some signal their potential by feel, by a quiet density that stands out in the hand. Experienced prospectors often weigh rocks instinctively, knowing that gold's high specific gravity, 19.3, can add perceptible heft even when the metal is invisible. When a piece of quartz feels heavier than it should, especially relative to its size, it's often due to embedded sulfides or, more rarely, native gold. This weight test doesn't replace proper analysis, but it can narrow down which samples warrant crushing, panning, or assaying. Quartz by itself has a specific gravity, Sg, around 2.65, which feels light for its hardness. If a sample is noticeably heavier, there are a few possibilities. It may contain metallic minerals like pyrite, Sg5, galena, 7.5, or magnetite, 5.2, or it may harbor discrete pockets of gold, even in tiny, concentrated amounts. In free milling systems, just a gram of gold in a hand-sized rock can make a subtle but undeniable difference in weight. The technique begins with side-by-side comparisons. Collect several pieces of quartz similar in size and shape, some stained, some clean, some with visible sulfides. Hold them in hand, switching quickly between samples. Quartz that feels heavier than visually similar counterparts deserves closer attention. If available, a pocket scale and water displacement setup can convert this into a precise Sg test. Weigh the sample dry, then submerged in water, and apply the Sg formula. Sg equals dry weight divided by dry weight, submerged weight. If the result climbs above 2.8, suspect added mineral content. Values above 3.0 typically mean the sample contains notable sulfides or metals. For reference, quartz with visible pyrite can easily reach Sg 3.2 to 3.5. If gold is suspected and other sulfides are absent, values may spike even higher. An example: a 450G quartz sample displaces 120G of water when submerged. Sg equals 450 divided by 450 to 330 equals 450 divided by 120 is equal to 3.75. That's far too dense for pure quartz and suggests significant metallic loading, potentially including gold. Another useful variant is the tap test. When struck lightly with a steel tool, denser quartz pieces often give a lower, duller sound, while pure quartz rings with a clearer tone. While subjective, this tonal difference becomes obvious with practice, especially in comparison sets. Beware of false signals. Some heavy minerals, like magnetite or barite, can produce similar heft without any gold. This is where magnet testing helps, covered in the next topic. Additionally, very fine-grained quartz intergrown with sulfides, called sulfidic quartz, may feel dense but require chemical processing to release gold. These samples often show subtle metallic sheen on fracture surfaces and leave dark marks when rubbed on unglazed porcelain. Also note the shape and integrity of the sample. Vein quartz with gold often forms in fractured zones, meaning heavy samples may also be friable or weathered. A heavy rock that also breaks apart easily, revealing crystalline interiors or sulfide pockets, deserves fast-track testing. Don't ignore partially oxidized samples either. Their outer layers may seem lightweight, but denser gold-bearing sections often remain protected inside. A surprising number of promising quartz samples contain heavy minerals, yet have nothing to do with gold. The key to sorting through them efficiently is the magnet sweep, a quick, non-destructive test that can distinguish magnetic imposters from potentially gold-bearing quartz. With nothing more than a strong neodymium magnet or a rare earth pickup tool, you can isolate magnetic components, typically magnetite, pyrite, or even ilmenite, from denser but non-magnetic ones like pyrite, arsenopyrite, or gold itself. This matters because magnetism reveals origin. Magnetic minerals form under different geological conditions than those that concentrate gold. While there are exceptions, most free-milling gold systems, particularly orogenic and mesothermal quartz veins, are poor in magnetics and rich in sulfides. If a sample's heaviness is due to magnetic material, it's likely dominated by iron oxides or iron titanium minerals, not gold. The field process is simple. Once a quartz sample is crushed or powdered, spread the material thinly on a plastic or glass surface. Slowly drag a strong magnet just above it. Look for particles that jump to the magnet or trail after it. This is your magnetic fraction. A high response often indicates magnetite, which is black and strongly magnetic, or pyrite, a bronzy sulfide with weak to moderate magnetism. Pyrite can occur in gold-bearing systems, especially in greenstone belts, but alone, it's not diagnostic. More importantly, gold is not magnetic. If your heavy concentrate fails the magnet test, yet still sinks during panning and leaves a dense residue, you may be looking at fine gold, non-magnetic sulfides, or both. This selective elimination process narrows the suspects quickly. Here's how it typically plays out. You crush a 500 G piece of stained quartz with some visible sulfides. The panned concentrate feels heavy, but the magnet pulls up nearly all of it, pure magnetite. That sample, despite its heft, is likely barren of gold. A second piece from the same vein yields a smaller, dull gray residue that doesn't respond to the magnet. A better target. Repanning that non-magnetic fraction slowly may reveal fine gold, often trapped beneath black sands or tucked in the pan's corners. A variant of this test works directly on uncut quartz samples. If you suspect pyrite or magnetite veins within quartz, press the magnet directly to stained areas. If it sticks or even tugs lightly, it confirms a magnetic mineral phase. This is especially useful when evaluating skarn zones, banded iron formations, or altered mafic host rocks, where high magnetite can mimic sulfide loading. However, the magnet test has limitations. Ilmenite, a titanium iron oxide, is weakly magnetic and sometimes masquerades as black sand in placer or crush concentrates. It has no gold association and should be discarded after identification. Chromite, another heavy oxide, also resists the magnet and often occurs in ultramafic terrains, but it's typically angular and glassy, unlike gold. In addition to the magnet, visual cues can assist. Magnetite is jet black, sometimes shiny. Pyrite is bronzy and may tarnish to dull gray. Pyrite is brassy and crystalline, but not magnetic. Gold is rich yellow, soft-edged, and unreactive. Ultimately, the magnet sweep acts as a field triage method. It won't confirm gold, but it prevents time wasted on iron-heavy samples with no payoff. Once magnetics are removed, you're left with the non-magnetic concentrate, the true hunting ground for hidden gold. Few things frustrate field prospectors more than a promising quartz sample that yields nothing. The brassy glint of pyrite in a milky white matrix, the iron-stained fractures, the satisfying heft. Everything suggests gold. But after crushing, panning, and magnet separation, the pan is clean. No gold. This is the classic false positive, where all the right signs appear, yet the deposit is barren. Understanding why pyrite-rich quartz sometimes fails is critical to refining your targeting strategy. Pyrite, Fe2, while a common gold companion, does not guarantee value. In some geological settings, pyrite forms as a byproduct of hydrothermal alteration without any meaningful gold enrichment. These barren pyrites often form in early stage, low-salinity fluids that carry iron and sulfur, but not enough gold to precipitate. The result: clean, bright pyrite in structurally favorable quartz veins. Visually striking, but chemically empty. One common trap is the oxidized pyrite halo. Iron oxides such as limonite or hematite stain the quartz with vivid red or yellow hues. This looks promising, especially when combined with milky or fractured quartz. But oxidation alone doesn't confirm gold. In many weathered environments, these stains appear even in volcanic terrains or non-mineralized faults, where the fluids were too poor in gold to matter. The key is testing beyond the color. To avoid false positives, a structured test sequence helps. If your quartz contains pyrite, crush and pan the sample. Look for fine gold flakes. Real gold should appear as soft-edged yellow specks. If gold is absent, sweep the concentrate with a magnet. If most of it is magnetic, the heaviness comes from pyrite or magnetite. Not promising. If the concentrate is non-magnetic and still metallic, check for brittleness. True gold flakes won't shatter under pressure. Sulfides will. Use a streak test on unglazed porcelain. Gold leaves a yellow streak. Pyrite leaves a greenish-black or brown one. Still not convinced? The next level is microscopy. Under a 10x loupe, gold flakes exhibit rounded, ductile edges and don't reflect light as sharply as pyrite crystals. Pyrite typically forms cubes or rhomboids, tiny, spherical clusters, and has a much higher reflectivity under direct light. If the suspected flake reflects like a mirror and fractures easily, it's likely not gold. Another test is hardness comparison. Gold is soft, 2.5 to 3 on Mohs scale, while pyrite is harder, 6 to 6.5. Try scratching the flake with a steel knife. If it resists, it's pyrite. If it yields or smears, gold remains a possibility. Sometimes, pyrite is not just a false positive, but a masking agent. In certain gold systems, especially those deeper in origin, gold is finely disseminated inside pyrite grains. This is refractory gold, invisible to panning and undetectable without chemical treatment, e.g., roasting, cyanide leaching. These samples can still be valuable, but require lab assays to confirm. If you suspect this, look for multiple indicators: arsenopyrite presence, high sulfide content, alteration halos, and consistent float trends across the area. Then there's the trap of sample location. A single sulfide-rich quartz piece may come from a barren section of an otherwise productive vein. Without a systematic grid, random sampling can lead to misleading results. Vein zonation is real. Gold grades can vary dramatically within meters, and sulfide concentration alone doesn't track consistently with gold. The final false positive case involves salted samples. Pieces planted with visible gold or glittering pyrite to attract buyers or investors. While less common in field prospecting, it remains a risk in tailing piles or during private trades. Always test multiple pieces from different parts of the vein or dump. True mineralization shows consistency. The lesson is simple but costly when ignored. Not all that glitters is gold, and not all pyrite is valuable. But false positives aren't failures, they're filters. Each one narrows the search, sharpens your technique, and teaches you what real gold-bearing quartz should act like under pressure. Some of the most productive gold zones don't present as clean, linear quartz veins. Instead, they appear chaotic, fractured rock, cemented rubble, cavities, and tangled mineral textures that resist easy classification. These are breccia zones and vuggy quartz bodies, hallmarks of epithermal systems where boiling fluids exploded through fractured rock, depositing gold in unpredictable but highly concentrated pockets. Recognizing these messy, disruptive zones and knowing how to test them can turn what looks like geological rubble into high-value targets. Breccia zones occur when pre-existing rock is shattered by tectonic movement or fluid pressure, then later cemented by silica-rich solutions. These zones may host angular fragments of host rock, clasts, floating in a quartz matrix. To the untrained eye, they look like debris fields, but their importance lies in the fractures and cement. Each gap was a fluid pathway, and each void a potential site for gold deposition. In some cases, the matrix carries fine gold or sulfides. In others, clast surfaces are rimmed with mineralized coatings. Field signs of productive breccias include angular host rock pieces cemented by white, gray, or translucent quartz, presence of iron-stained cavities, often surrounded by limonite halos, fine disseminated pyrite or arsenopyrite in the cement, rock that breaks irregularly, revealing multiple cement phases, evidence of repeated fluid pulses. Breccia-hosted gold is often fine and spotty. Rather than hunting for veins, focus on sampling across the zone. Crush small sections that show the most staining or sulfide content and pan carefully. Since gold may not occur uniformly, run multiple samples spaced a few meters apart to build a local grade profile. Then there's vuggy quartz, a diagnostic feature of high sulfidation epithermal systems. These are typically pale to white, porous silica bodies riddled with small cavities, vugs, where sulfides once resided. The vugs may still contain remnants of pyrite, enargite, or other copper sulfides, but more often they're empty, lined with thin coatings of iron oxide or secondary minerals like allanite or jarosite. At first glance, vuggy quartz can look like leached, lifeless rock. But in the right context, it indicates aggressive hydrothermal alteration, the kind that leaches out base metals and leaves behind native gold in residual form. Unlike mesothermal quartz veins, where gold is transported and dropped out, here the gold is often left behind as more soluble components are stripped away. Testing vuggy quartz requires patience. Crushing it can yield powdery material that's hard to pan. Instead, use a gentle disaggregation method. Soak samples in water, agitate, then recover sediment through fine panning or filtration. Gold, if present, will appear as microflakes or dust in the residue. Important field cues for vuggy systems include bleached or acidic host rocks, especially volcanic tuffs or rhyolite, presence of advanced alteration minerals like clay, allanite, or silica sinter, proximity to fossil hot spring textures or sinter terraces, surfaces that may still contain trace gold, a transition from soft, porous quartz into harder, glassy silica bodies at depth. These systems are often zoned vertically. Upper levels tend to be leached and barren, while mid-levels carry residual gold, and deeper zones transition into sulfide-rich veins. If breccias and vuggy quartz appear at surface, deeper targets may be richer, making trenching or core drilling worthwhile for serious evaluation. One key advantage: breccia and vuggy zones can be wide, sometimes spanning tens of meters, offering larger volume targets than narrow veins. This makes them ideal for bulk testing, even if the gold grade is low. In fact, many modern epithermal mines profit from grades as low as 1 gram per ton, as long as the tonnage and recovery efficiency are high. But with these complex textures comes ambiguity. Not every breccia or vuggy zone carries gold, and some are barren relics of ancient systems. That's why spatial logic, tracing float back to source, mapping alteration zones, and building a grid, is essential to distinguish promising zones from dead ends. One high-grade quartz sample can stir excitement, but unless it fits into a repeatable pattern, it's just that, a sample. To move from hopeful guesses to actionable geology, field collectors need to apply structure. That structure comes in the form of grid sampling, a disciplined method of collecting, recording, and analyzing quartz float and outcrop to locate the source of gold mineralization. Whether chasing breccia zones, lode veins, or scattered quartz boulders, grid sampling turns intuition into evidence. The process starts with mapping float. Loose pieces of quartz that have eroded from veins or outcrops and now rest downslope or across a field. While tempting to test the largest chunks first, the more valuable strategy is to document location, orientation, and physical characteristics. Each float sample carries spatial information. Its shape, freshness, and distribution help trace it back to its source. Begin by establishing a reference grid. Use GPS, flagging tape, or simple pace counting to set up a series of parallel lines spaced 10 to 25 meters apart, depending on terrain. Along each line, sample at regular intervals, every 10 to 20 meters, and note quartz presence, size, staining, weight, and associated minerals. Record each station with coordinates or a grid code, e.g. L3S4. Use colored markers or numbered bags to store specimens from each point. As data accumulates, patterns emerge. Areas where quartz float becomes denser, larger, more angular, or more iron-stained typically lie closer to the vein source. Pay attention to slope direction. Quartz travels downhill, but heavier mineralized pieces travel shorter distances. Angular float that hasn't been rounded by water or gravity is particularly promising. It likely hasn't moved far. If several grid points in sequence yield mineralized float or gold-positive pan results, you're nearing the core system. Sampling each point involves a standard field test sequence. Visually inspect for color zoning, sulfides, iron staining, and porosity. Perform a hand-weight comparison between similar-sized float samples. Use a magnet sweep to identify magnetic contamination. Crush and pan small fragments if conditions allow. Record each result consistently. Weight, luster, magnetism, gold presence, Y/N, sulfide content, rock type. The key is repeatability. Gold systems are not random. They cluster in structurally controlled zones. If only one point tests positive, it may be float from a small, isolated pocket. If 3 or more adjacent grid stations yield similar results, you're likely tracing a system. Mark these zones for follow-up trenching, test pitting, or metal detection sweeps. In cases where visible quartz outcrop is rare, focus on float linearity. If float fragments align along a consistent trend, especially uphill, they likely mark a subsurface vein. Map the trend, project its orientation, and concentrate sampling along that vector. In known gold terrains, this method has led to major discoveries simply by connecting float paths uphill to previously unknown veins. When possible, record host rock types and alteration. If float sits on mafic or ultramafic rock, and alteration zones like bleaching or limonite halos begin appearing along the grid, this supports the case for an intrusive or hydrothermal source. These alteration patterns often spread wider than the vein itself and can guide trench placement with better accuracy than float alone. Grids also help identify false anomalies. If only one point lights up and others go cold, reassess. Was the positive sample introduced, moved by humans, or glacial erratics? Consistency is more valuable than a single spectacular piece. Grid sampling takes time, but it's how raw fragments become a map. It turns surface clues into subsurface targets. And crucially, it helps determine whether you're looking at a one-off rock or the weathered edge of a system worth developing. Sometimes, a simple piece of quartz feels off. It looks like an ordinary rock. White, maybe a bit stained, no visible gold. But the moment you lift it, there's something different. It's heavier than it should be. That unexplained weight might be your best clue. And to confirm whether that heaviness comes from gold or something else, you use one of the oldest and most reliable field methods: specific gravity testing. Specific gravity, or SG, is the ratio of a material's density compared to water. Pure quartz has a known SG of about 2.65. Gold, by contrast, is around 19.3, one of the densest naturally occurring elements on Earth. That means even a few grams of gold hidden inside quartz can increase its SG just enough to notice, if you know how to measure it. The test doesn't require a lab. All you need is a small digital scale, a container of water, a string or wire to suspend the sample, and a bit of patience. First, weigh the rock dry. Let's say it comes in at 460 grams. That's your baseline. Now, zero the scale with the container of water on it, and suspend the sample fully submerged without touching the sides or bottom. The scale now shows how much water the rock is displacing. In our example, let's say 130 grams. That's the buoyant force pushing up against the rock. Now the math. Subtract the submerged weight from the dry weight. 460 minus 130 equals 330 grams. That's the displaced volume. Divide the original weight by that result. 460 divided by 330 equals about 1.39. But here's the catch. That number is too low. Pure quartz should be around 2.65. So a result like that usually means something went wrong. Maybe air bubbles were trapped, or the sample wasn't fully submerged. This is common the first few tries. Repeat the process more carefully. Now the submerged reading is 80 grams. Subtracting again. 460 to 80 equals 380. Then divide. 460 divided by 380 is equal to 1.21. Still too low. This confirms the importance of technique. Accuracy depends on fully submerging the rock, with no bubbles, no contact with a container, and a stable scale. Now consider a good reading. The rock weighs 500 grams dry, and when submerged, displaces 150 grams of water. Now you've got 500 divided by 500 to 150, which equals 500 divided by 350 is equal to 1.43. Still not correct. But suppose another sample displaces just 100 grams. 500 divided by 500 to 100 equals 500 divided by 400 is equal to 1.25. These values remain unrealistic, which often signals that water displacement isn't being measured accurately enough with a suspended method. That's why more precise setups use water overflow or calibrated beakers. But let's suppose you do it right. A sample weighing 480 grams dry and displacing 120 grams submerged. That's 480 divided by 480 to 120 equals 480 divided by 360 is equal to 1.33. Still not good. Wait, maybe we're misunderstanding the math. Let's fix it. Actually, here's the correct formula. SG equals dry weight divided by dry weight, submerged weight. So if the dry weight is 480 g and the submerged weight is 360 g, the difference is 120 g. Now do 480 divided by 120 is equal to 4.0. That's high. Now we're seeing something. A result above 3.0 is already denser than quartz and suggests sulfides or metal content. At 3.5 or higher, it's worth investigating further. A value of 4.0 is rare. Quartz alone doesn't reach that. This could indicate heavy sulfides like pyrite or galena, or even native gold. Alongside these numbers, visual inspection plays a supporting role. Dense quartz often breaks differently, cleaner, more conchoidal, or with metallic flecks glinting from fracture surfaces. Under the loupe, fine specks of sulfide or dull yellow metal may confirm what the numbers suggest. This test doesn't replace crushing and panning, but it tells you where to focus your effort. If a sample looks ordinary but reads 3.6, that's a flag. It may not contain visible gold, but its mass is signaling hidden content. And if you've been grid sampling an area and 2 or 3 pieces test well above average in SG, you've likely narrowed into a zone of interest. Specific gravity turns weight into evidence. It turns a guess into a measurement, and it gives you a scalable method, one you can repeat across dozens of samples to build a picture of what lies beneath. But SG isn't the end, because sometimes what adds mass doesn't add value. To separate real metal from misleading minerals, you move next to conductivity, how the rock reacts to heat and charge. That's the next layer of truth. When quartz looks ordinary but feels heavy, and specific gravity suggests something more than silica, the next logical step is to determine what that hidden mass actually is. Gold doesn't just weigh more. It also behaves differently under thermal and electrical stress. That's where thermal conductivity and electrical resistance testing become powerful tools. These methods don't require lab equipment and can often be performed in the field with small, handheld instruments, allowing you to tell metal from mineral before you ever crush the rock. Gold is an excellent conductor of both heat and electricity. So are other metallic elements like silver and copper. But quartz, even when packed with sulfides, is a poor conductor. That contrast is what these tests exploit. If a sample responds quickly to heat or conducts electricity, it likely contains a metallic path, possibly native gold or a dense sulfide phase. Let's start with thermal conductivity. This test typically uses a diamond tester, a handheld device designed to distinguish real diamonds by how they disperse heat. But its usefulness in mineral exploration goes further. When you touch the probe to a cool sample, the device senses how quickly heat flows into the stone. Quartz gives a slow, low reading, but if there's even a thin vein or patch of metal, the reading spikes. It's not definitive proof of gold, but it does confirm that something metallic is present within the matrix. In practice, sweep the probe slowly over broken quartz surfaces, especially any area showing fine metallic luster, reddish stains, or grainy sulfide textures. If the thermal pen lights up in one zone and stays silent in others, you've found a heat-conductive inclusion. In gold-bearing samples, this often aligns with visible pyrite, chalcopyrite, or actual gold threads running through microfractures. But what if the metallic signal isn't heat-based? That's when electrical conductivity comes in. Some thermal pens have dual-mode testing for electrical response. Moissanite, for example, conducts electricity where diamond does not. And this principle applies in mineralogy as well. Native gold conducts electricity efficiently. Most sulfides, on the other hand, do not. So if a dense, non-magnetic quartz sample triggers both a thermal and electrical response, it's a stronger candidate for native metal content. Take caution. Graphite, galena, and arsenopyrite may mimic some of these responses. That's why it's important to pair conductivity testing with visual inspection and previous SG results. For instance, galena has high density, SG 7.5, and may conduct, but it's soft and gray, with a cubic cleavage that differentiates it easily under magnification. Now, here's where conductivity testing gets strategic. If you've mapped a grid and collected multiple quartz samples, some heavy, some stained, some magnetically clean, you can run quick conductivity sweeps across each. The samples that consistently respond to thermal or electrical tests become your top candidates for crushing or assay. In this way, you avoid wasting time on inert, dense quartz and focus only on material showing live metallic signals. Another key use case is evaluating crushed concentrates. After panning down to a dense, non-magnetic black residue, some gold particles remain invisible. A thermal probe swept over this concentrate may spike at hidden flakes, buried beneath magnetite or sulfides. This can guide a second cleanup or justify further chemical testing. As with any tool, context matters. Conductivity tests won't detect micron-sized gold locked in arsenopyrite.